Okay, we got a couple more business problems on this page, page 11 of applications of calculus. So, a manufacturing company makes door hinges. They have a standing order filled by producing 50 per hour, but production of more than 150 per hour is useless as they will not sell. So basically their domain is 50 is less than equal to x is less than or equal to 150. Okay, the cost function for making x hinges per hour is, so this is a per hour cost, and the input is how many hinges they are making per hour. Okay. Oh, here they wrote this here. Okay. Find the minimum maximum hourly costs and the production levels where each occurs. Okay, so they already gave us a cost function per hour. So they're just saying find the minimum maximum points on this C function, which is basically saying find the derivative, set it equal to 0, find when the derivative equals 0, and then classify it into mixed minimum or maximum. So, okay, let's do that. So as usual in the calculus chapter, we are going to take the derivative of a function. It'll be 0.00073x squared. It'll be negative 0.17962x, and then plus 14.663, and just we remove the x, and the 160 of course becomes 0. This is the derivative function. Just simplifying, we're going to put 0.0021x squared. 0.1796 would be 0.1796 times 2 is equal to negative 0.3592x. And then the last one is going to be 14.663. So all I did here was rewrite the first derivative function, right? And I'm going to use the first derivative function to set it equal to 0, and then find out what the x value, which makes that maximum or minimum. And then I can use the second derivative function, which would be 0.00212x minus 0.3592 to figure out which x values give minimums and which give maximums. So just to simplify here, it'd be 0.0042x minus 0.3592. Just to see where the transition occurs between minimum and maximum, I set this equal to 0. It'll be 0.0042x equals 0.3592. X equals 0.3592 divided by 0.0042, which is equal to 85.5. So this is 85.5 is on the second derivative sign diagram. It is the point where the second derivative is 0, so the concavity, there's an inflection point between concavities. If I put a big positive number in here, I would get a positive number out for the second derivative. If I put a big negative number here, I would get a negative number out. So basically here it is concave down, and here is concave up. So now let's figure out where the x values which make this 0 occur. And that, of course, we're going to use quadratic formula, but instead of using quadratic formula, why don't we just use poly-SMLT? Okay, so we're just going to type in 0.0021 for the a value, negative 0.3592 for the b value, etc. So, order 2, next. Okay, so we're going to put in 0.0021 for the a value, negative 0.3592, negative 0.3592 for the b value, and 14.663 for the c value, and we solve it. And let's change it to decimal by pressing this button. So one of the values is x equals 103.7. The other value is 67.3. Which one's minimum, which one's maximum? Notice that 103 is over here in the positive concavity region, so that would be a minimum. And then 67.3 is over here in the negative concavity, so that would be a maximum. And So we found the minimum, we found the minimum and maximum X values. Now we need to plug it in to, so these are the production levels. So that we found the production levels where the minimum maximum occurs. Now we just need to find the cost at 103.7 and the cost at 67.3 of the C function. Okay, and to do that, we probably would just put the function, the C function, in the calculator. I'm just going to type that into y equals, and then I'll find out what the values are at 103.7 and 67.3. I'm just going to pause the video while I type it in. Okay, I just typed the function in, and then I'm just going to graph it. And then I'm just going to do second. I'm sorry. I'm just going to do trace. Oops. I'm going to graph it, and then I'll do trace. Where's trace? Trace. And then I'm going to type in 103.7, and then I'm going to find out what my cost is at 103.7. It is, and it's the minimum point as we can see here, 529.80. So the cost is it dollars? I don't know if it says, but okay, so the cost is going to be 529.80. Okay, and then at 67.3, it would be trace 67.3, and then that cost would be 546.73. Whenever you give a money cost on the IB exam, give decimals. Now, while we were checking out the minimum and maximum, these are local minimum and maximums, right? They want to know what the minimum and maximum hourly costs are within this interval. Notice that even though this is the local maximum and it's the highest point in this small neighborhood, look what happens after this minimum point. It starts going up, right? And we don't know exactly where this cuts off. What if we adjusted the window so that it's on this domain? We're going to do it between 50 and 150 for x min and x max, and we'll do that so that we'll see if there are any edge values which are actually higher than the local minimum and local maximum. Ooh, let's do zoom fit. That'll help. Zoom fit 0, I think it is. Okay. Whoa, look at that. So this is the interval that we should be studying. The minimum value is the local minimum that we found, but the local maximum is not the highest value. We need to get that value right there. What value is that? Well, this x value is 150. What is the y value at 150? So we'll just do trace 150 to see what that cost value is. It's 680.95. So actually, the maximum cost in that interval is going to be for 150 hinges. Okay, so 150 hinges has this maximum cost. So this is like the value at the boundary. Okay, so we need to look at that also to make sure that it is not higher or lower than these two values. What about this value here? So this value is 50, so we'll do trace 50 just to see, make sure that that's not lower than the minimum value. 531.65. Okay, so that's slightly bigger than this minimum value. So the minimum value here is going to be this, and the maximum value is going to be this global maximum here, 680.95, which occurs at the edge. And the only way to find that is to simply plug in the edge values 50 and 150 into the function to see what those values are, to see if they're higher or lower than the local minimums and local maximums. Okay? All right. Number 11. Consider the manufacture of cylindrical tin cans of 1 liter capacity where the cost of the metal used is to be minimized. This means that the surface area must be as small as possible. Explain why the height is given by blah, blah, blah. Okay. we have a cylinder, and we are trying to make an equation for surface area because we're trying to minimize that. What is the equation for surface area of a cylinder? So basically it is pi r squared from the top, pi r squared on the bottom, and then this lateral piece is going to be 2 pi r around. Okay, so 2 pi r around, and then h high. So basically the surface area of this lateral piece is going to be 2 pi r h. So we're going to add these three things together, and that would give us 2 pi r squared plus 2 pi r h, and that is the total surface area. Okay. We know that the volume is 1 liter. So the volume of a cylinder is given by pi r squared h, and that is 1 liter. Okay, or 1,000 centimeters cubed. Okay, 1 liter is 1,000 centimeters cubed, by the way. Okay, and if we want an expression for h, we could just isolate h here, and notice that it would be 1,000 divided by pi r squared, which is the expression that we were trying to demonstrate that h is equal to. The reason why it is this expression is because we're holding the volume constant. So if we make a volume equation here and we isolate h, we end up with that. Okay. The total surface area is going to be, oh, we already did that, 2 pi r squared plus 2 pi r h, but we would like to put this h function into here so that we have everything dependent r and r only. So I'm going to do that. I'm going to write a equals 2 pi r squared plus 2 pi r. Instead of h, I'm going to put 1,000 divided by pi r squared, and then the pi's cancel out. One of these r's cancel out, and we end up with 2 pi r squared plus 2 times 1,000, so it's 2,000 divided by r. Does that match? Yes, it does. Use technology to help you sketch a graph of A against R. So let's graph this. We're going to put this into y1, this expression into y1. So we'll do y equals, and then I'm going to type in 2 pi r squared, so x squared, and then plus 2,000 divided by x, and we're going to graph that and sketch it. So I'm going to put the domain as, I don't know, 0 to, let's see, there's some things that are 1,000 here, so I'll do 0 to 1,000 for x. Actually, the x value is r, so the r value is not going to be 1,000. It's probably going to be more like 100, so I'm just going to put 100. And then for the y values, I'm going to put 0 to 1,000 because the volume and the area seem to be like in the thousands. Graph. Okay. I'm not sure if I graphed enough, but okay. So it looks like there's a minimum point there. Is that what we want? A minimum? Yeah, we want a minimum point. So we're going to use technology to draw the graph. Looks kind of like that. Kind of like that, I guess. And find the average, find the value of r, which makes a as small as possible. We could do that with the derivative, right? So let's do that with the derivative. We're going to take the derivative, and so we're going to set it equal to 0. So a dash is equal to 4 pi r plus, and we can rewrite 2,000 over r as 2,000 r to the negative 1. So the derivative would be negative 2,000 r to the negative 2. And then we can set that equal to 0. So we'll have 4 pi r minus 2,000 over r squared equals 0. Multiply everything by r squared so that we can get that out of the denominator. It would be 4 pi r cubed minus 2,000 equals 0. multiplying r times 0 does nothing, or r squared times 0 does nothing, right? And then we can solve for pi r squared by r cubed by isolating the r cubed. R cubed is equal to 2,000 divided by 4 pi, and then we can cube root that. 2,000 divided by 4, by the way, would be 500 divided by pi. So cube root of 500 divided by pi is the value. So let's just go ahead and do that. We'll do cube root. Cube root would be math. Then you go down to cube root. And then inside we're going to put 500 divided by pi. And the answer is 5.42. The r value is 5.42. Alrighty, find the value of r which makes a as small as possible. Sketch the can of smallest surface area. Well, it kind of looks like that. We're just going to put dimensions on it though. So it would have a radius of 5.42. And then what would be the height? We can find the height because we have this equation which relates radius to height. We could say the height is 1,000 divided by pi times 5.42 squared. And so if we put that in the calculator, we would have 1,000 divided by pi divided by 5.42 squared. 5.42 squared. Enter. And so it'd be 10.8. 10.8. So then our height is 10.8. That's our sketch. It didn't ask us for the area, but if we wanted the area, we could put r equals 5.42 back into here, right? We could have 2 pi 5.42 squared plus 2,000 divided by 5.42. Oops, 5.42. So 554 is the area. Is it the area? Yeah, the area. So we can make our sketch a little bit better by saying, oh, at this minimum point here, the r value is 5.42, right? And the area is 554. Okay, that's it.